Welcome, everyone. Today we are talking about new ideas in cosmology. Many of you have been witnessing conversations we've had over the last few months, really last few years, on ideas in cosmology, the familiar notions of inflationary cosmology. We've spoken about some of the more recent proposals having to do with cyclic models of the universe and exotic ideas of that sort. And today we will be taking up another new idea, one that is really at the edge of our current thinking about things. But if the ideas that will be presented to you by Neil Turok are correct, they really will, in a sense, upend 40 years of thinking in cosmology. So it's exciting and well worth the risk that any new idea faces, which is it may not be correct, but it's exciting to hear ideas at the forefront. So I'm so excited to bring in Neil Turok, who is the Higgs Chair of Theoretical Physics at the University of Edinburgh. He's the Emeritus Director of the Perimeter Institute for Theoretical Physics in Canada. Prior to that, he was Chair of Mathematical Physics at Cambridge and Professor of Physics at Princeton. And he joins us from his office in Scotland. So welcome, Neil. So good to see you.
Thank you, Brian.
Yeah, I was just thinking, again, many of these conversations are with people that I don't have a particularly long history with. I think we probably go back, excuse me, what is it, like 40 plus years or so. I think you taught me at like a summer school, if I can remember correctly, right? Isn't it
That's exactly right. There were you and Kelly Kirkland, who
ah,
were graduate students at Oxford, and you had just done this really interesting work finding realistic compactifications of string theory. And you came to my lectures in Erice, and
yes.
since then you've done pretty well. So I take full credit.
and well deserved. It was inspirational to hear your lectures for sure. And so, what I want to do today is give the audience a feel for some of the new ideas that you and your collaborators have been developing. But if it's okay with you, I'd like to put it in context because in this program, we have had a lot of conversations with people like Alan Guth and Andre Linde and Andreas Albrecht and the old guard, if you will, of inflationary cosmology. We've also had Paul Steinhardt,
Yep.
who you and he developed a cyclic model of the universe, which
Yes.
was exciting to you for a while, but
Yes.
you've now moved on to other ideas. But I'd love to the audience to get a feel of that trajectory.
Sure.
So going right back to the inflationary theory, in the early days, presumably you found that at least compelling enough to put a lot of effort into working, on the fluctuation spectrum of the microwave background and things of that sort. So, can you give us a feel for how you responded to the inflationary idea back, say, 20, 30 years ago, if not more?
So I was very lucky to attend the first big workshop on inflation held in Cambridge, 1983, I believe. And I was a graduate student, or maybe it was 82. I was a graduate student in London, and I went up to Cambridge for the day and saw Guth and Linde and Hawking talk about, very excitedly about this approach. I must admit, I've always been a little bit skeptical um, from that time. Uh, to be frank, the participants in this workshop did seem to be making it up as they went along, which I think is a sign of excitement. That's a great thing where you see a field in the process of its formation. Um, and so there were different pictures of inflation, and some people claimed it would give the fluctuations, and others that it wouldn't, and so on. It took a few years to really settle down. Um, but what I did not like about it was the fact that there were so many models right from the beginning. And more or less every grand unified theory or supersymmetric theory anybody had invented was immediately put into work as an inflationary model. And I was always hoping for something more than that, something more compelling, more principled. I think of inflation as a phenomenological model. It's a sort of story which at least is consistent with what we see, but doesn't really explain much about what we see
Right.
from a principled point of view. So I was uneasy about it. And I guess, part of it goes back to my own background. My parents were political activists in South Africa. And, they decided the system was wrong. The apartheid system was wrong, and they dedicated themselves to changing it. And I was very inspired by their story and their history. And they both ended up in parliament in South Africa, having been, in prison, both of them. They end up in parliament. And so what I learned from them is, if you are uncomfortable about something or you don't believe something is right, um, stick up for what you do think is right, and don't be afraid of that. So I wasn't afraid of resisting the consensus in cosmology. It became very strong. I always was a bit contrarian. So people claimed, for example, that inflation inevitably produced a flat universe, a spatially flat three-dimensional universe. Um, but looking at the papers more carefully, historical papers about inflation, I realized that, Sidney Coleman and others had in fact envisaged how to get an open universe out of something very like inflation. And Guth had ruled this out, but for reasons which turned out to be spurious. And so I developed a sort of contrarian picture of inflation, in which inflation resulted in a curved universe. Um, and so I thought that was an interesting sort of alternative viewpoint. And it's really important in cosmology, probably more important than any other field of science, to have competing models, because you can't really judge the correctness of an idea unless you show there are alternatives which you have clearly proved wrong. So
Right.
for me, that's really important, and too few people work on developing alternative models which are testable, and from testing them we'll learn something. I mean, I basically feel that all these models will be extremely lucky if any one of them is anywhere close to reality. You have to have a lot of chutzpah to believe your ideas are actually right about the beginning of the universe. So I love playing with these ideas, but I think we've really got to try to subject ourselves to the most rigorous tests we can. And my uneasiness with inflation was that I don't think people have been doing that harshly enough.
So I want to get into some of the details
Sure.
of your discomfort, but more generally, I mean, do you find that the scientific system, the way that we award tenure and things of that sort, does it too much promote a kind of herd mentality that some people speak of, that sort of one idea sort of rises up and then everybody jumps upon it?
Absolutely. And it's getting worse. I was very fortunate to get into physics in the early 80s, when there was much less insecurity in the field. There was a culture of, we'll do this, and if it's fun, it'll work out. And if it isn't, we'll do something else. I always had in the back of my mind that if physics didn't work out, I'd go and be a wildlife ranger in East Africa, and
Oh,
that
is
was,
that right?
yeah, that was such an appealing thought. I thought, I'm not worried. So I never worried about tenure or anything like that. And in fact, I used to have a nightmare when I worked at Imperial College, that I was walking down the corridor and my name was on one of the offices. I woke up in a cold sweat. Oh my God, is this my
Whereas for
future?
some people, that would be, nirvana. Right?
Exactly. So yeah, I think it's very worrying.
Yeah.
Young people face so much pressure now to conform and do something which will be quickly recognized and assimilated into the sort of body of knowledge. So yeah, I try to encourage young people as far as I can to
Yeah.
be a bit more adventurous.
Yeah, I remember you and I once went for a long walk. I don't know if you remember in Stellenbosch.
Okay, yes, I do.
Remember there was a
Yeah,
summer school of some sort, in
yeah,
South Africa.
that's
And, I remember, feeling this deep love for the land, as we walked around, coming from you, which was,
yes,
I
yeah,
can well imagine how heading off to East Africa as a wildlife ranger would have it feel.
exactly, exactly.
But on the physics front, so in inflation, however much it may have been, and perhaps it, to some extent has continued to be one of those arenas that has drawn people simply because it has drawn people,
Yeah,
that sort of
yeah,
accumulative effect.
yes,
There are things about it that do feel compelling, at least when presented in the right way. This
yeah.
idea of, how do you get two distant points in the sky to be at the same temperature? Well, allow them to stick around close together longer early on and then rapidly move them apart, and you can get them at the correct distance, and yet they will have interacted enough to equalize their temperature.
That's right.
How do you get it to be nearly flat? You're saying it doesn't necessarily have to be,
Right.
but there are certainly models where,
Yeah,
if you expand, the earth large enough, it looks flat, right?
yeah.
So if you expand the universe enough, it will look flat by sort of similar reasoning. So, do you find that these are no longer as compelling explanations because there are alternatives, or did you never fully believe those in the first place?
No, I think they are very strong arguments, and I think inflation was indeed a wonderful idea. That's the evidence for that is clear. It drove a whole generation of experiments because this was a reasonably well formulated theory where you could compute. I wouldn't call it a theory. I'd call it a
Framework,
a
maybe, right?
framework. Yeah, it's not
Yeah.
quite a theory. I mean, Guth himself called it a scenario. It's not really a theory. It's a framework collection of models. But you could do very clear calculations and make predictions for experiment and then check them. So it did drive a whole generation of experiments, very, very productive framework, which I think supported a huge amount of observational progress. Yes, it is I mean, I think the point you mentioned about solving the horizon problem, why the universe appears the same in opposite directions, is important. Equally important, just the large numbers. The universe seems to have a lot of stuff in it. And the basic idea of inflation is that you can take a small universe and blow it up exponentially. Uses this property of Einstein's gravity that energy is not conserved, that you can make more and more of it during inflation. So it explains large numbers simply by, as exponentials. And so I think that's a very important argument in favor of inflation. However, I would say that where inflation fell short is it was intended as a solution of what we call the measure problem, namely which spacetimes are more likely than others. So inflation somehow made a big, smooth, flat universe more likely than a small, lumpy, curved one. Um, but the problem is that inflation never really resolved what the measure is. It was always to some extent ad hoc, that you postulated a small, lumpy universe, but you also postulated it was full of inflationary material, and that would blow itself up. But you can never really explain what initial conditions were more likely than others. And so, people like Roger Penrose, who I was very influenced by, argued that this really wasn't a solution at all. It's just a sort of postponement of a really important problem. Why is the universe so incredibly simple on the largest scales we can see? So Penrose, wrote about this in the 70s and 80s, 80s especially, very critically of inflation, I think 1987. And as usual, Penrose never wrote down much maths, although he's the best mathematician in theoretical physics. These were all words, okay, and so I was quite influenced by that, and so in thinking about this measure problem, what geometries are more likely than others? Somebody who attempted to tackle that head on was Stephen Hawking. And so he had this very specific, beautiful proposal called the no boundary proposal, which is supposed to resolve the Big Bang by smoothing it off into a regular geometry without a singularity at all. And Hawking allied his proposal to inflation. So Hawking, to his credit, was really trying to solve the measure problem in inflation. And I was very taken by that. So as it happened, I moved to Cambridge shortly after we'd invented this open inflation picture, which was really, as I say, a sort of contrarian picture, just to show, oh no, it doesn't predict a flat universe. And I went there and gave a talk about this, and to my delight, Hawking became interested. And so then we talked a lot. And I kind of got to understand his vision for how the universe might have begun in this smooth and predictable manner, in this no boundary proposal. So I was very influenced by that. I worked on it for quite a number of years, partly with him and partly with others. And in the end concluded it just didn't work. It was a very elegant proposal. It is a very elegant proposal, but it predicts an empty universe. It predicts that you sit in the minimum potential energy state, not the inflation state. So a lot of people have worried about this.
By the way, did Stephen ultimately agree with that, or what
Yes,
was
I
that?
mean, Stephen was a really good scientist, I would say. I mean, it's very hard to. He actually thought of this no boundary proposal as his best idea ever. And he was very, very proud of it because it was so elegant. But when we started to show that the predictions were, the opposite of what he hoped, he was very generous. So he invited me to retreats. He had wealthy supporters who paid for private retreats in rather beautiful, houses, old houses and castles in England. And he held several such retreats, and so he invited me, and we had discussions among small groups of people. Um, and Stephen was always very, I would say, very willing to listen to criticisms and problems. And he would always engage with arguments in a fresh way. You told him something, and he wasn't bringing all of his enormous insight and intuition to it. He would just deal exactly with what you said in a very straightforward way. So it was really great fun. So I don't think he ever accepted publicly that this was a real problem, but he never put his name on a paper disputing our claim that the consequence was an empty universe. Now, so I was impressed with Hawking's idea and uh, and the motivation behind it.
Would you say that Hawking's idea, in some sense, breaks the usual paradigm of laws and initial conditions?
Absolutely, absolutely. That's exactly right. His picture was that the laws would define their own initial conditions, and this was a sort of self-contained theory that, yeah, predicted itself in a certain sense, predicted the physical reality, including initial conditions. And so, whereas I think his collaborator, James Hartle, always stressed the difference, that you needed a theory of both, Hawking just wanted one theory, which somehow inevitably produced the universe as we see it,
Which
uh,
would be beautiful if you
which
make
would
that.
be absolutely beautiful. So, this always stuck with me, his vision of how physics should work. Um, and then came the observations, um, partly motivated by testing inflation. The observations got more and more precise, and what they revealed was more and more surprising. The universe is stunningly simple. It requires just five numbers to fit everything we see on the larger scale. There are three numbers that tell you the proportion of the different kinds of matter. There's ordinary matter, the nucleons and atoms we are made of, nucleons and electrons we're made of. Then there's the dark matter, which, sounds like a fudge initially, but actually works amazingly well in fitting the data. A very simple kind of dark matter fits extremely well. And then finally, there's the cosmological constant, which again is extremely simple, dates back 100 years to Einstein, and seems to be there and dominates everything. So three numbers for the matter or energy content, and then just two numbers for the fluctuations. You require an amplitude and a
And tilt.
small spectral tilt,
Yeah.
which I think is a critical exponent. In condensed matter, these are very familiar, these small tilts. And so it seems that the universe, that's it. These five numbers, you explain every observation that has been made so far. There are discrepancies, there are claims that things go wrong, but they're all at a level which is not yet convincing. Whereas there's a huge weight of evidence in favor of the general picture. So, so, when as these observations got more and more refined, and by the way, they do not show any evidence of a sort of smoking gun of inflation, which is the gravitational waves that this exponential burst produces. So again, Stephen's attitude was inflation's probably right. I mean, he was invested in it because he did some of the first calculations and hosted the first workshop on inflation. So he was invested in it, but he said, look, I'm going to stick my neck out and say we will see gravitational waves from inflation at a certain level. So I had a bet with him. He didn't have a very good record of winning bets, but to his great credit, he was willing to do it. And so he made a bet that the Planck satellite will see these gravitational wave signals in the cosmic microwave background, which it hasn't. And progressive as the experiments have progressed, the limit has come down and down, and now it's well below what Stephen anticipated. And in the next,
Now, proponents will say that it's one of the free parameters of the range of inflationary models that the amplitude of those gravitational waves could just be too small. Do you feel that's just a fudge, or that
it's the nature of inflation. It's a framework. It's not a model.
Yeah.
So the advocates will tell you, I don't mind if most of the models get ruled out as long as one of them works. And that's all we need to explain the universe. Well, I disagree. And I think, unfortunately, theoretical physicists, as clever a group as they are, sometimes overlook the most elementary things. And one of them is statistical inference. We are not trained in proper statistical inference. Okay.
We meaning we physicists,
Yeah.
you mean?
Yes.
Okay.
There is too little attention paid to understanding what probabilities are in our background. We don't really have in-depth courses in statistics, probability, and inference, which is a fancy field, and it's a foundation for good statistical analysis of all kinds of data. So we're not very good at that, and I think that makes us blind to certain weaknesses in our theories. So when you have a framework, and it's not a theory, but there are many, many possible models, and you start testing it, and you find, one or several models that fit, but many which don't, you can't just disregard the ones that don't. You need to give a posteriori probability for the framework. Was the framework, how strongly do you favor or disfavor the framework given that you've ruled out 90% of the models. Well, you lose. You lose. Your posteriori probability for the framework is only 10% if 90% of the models got ruled out. Sorry, it gets de-weighted. And that de-weighting has happened progressively with inflation.
But can I ask you about that? Because maybe I'm one of those physicists that is not sufficiently well versed in statistical or probabilistic thinking. But if you were to apply that same reasoning to, say, quantum field theory, so we have the standard model of quantum field theory. It has a certain, if we speak technically for just a moment, it's a certain symmetry group. SU3 cross SU2 cross U1 for the people in the audience that are familiar with the math. There are many, many other possible gauge groups. There are many other possible representations of matter content and so forth. Couldn't I say that 99% or even
More.
more of those more were ruled out?
Yeah.
And so wouldn't I then distrust the gold standard of physics, the standard model of particle physics, if I was to follow the same?
No, you would say that the quantum field theory framework is not a good theory for fundamental physics. You would say that there is a quantum field theory which works, but the framework as a whole doesn't describe reality.
But then why can't I say the same thing with inflation? Like the inflationary framework,
Yeah,
there's too many models.
yeah,
But if we find one inflationary model
yeah.
that really does work, then wouldn't I be in the same
No,
position?
not unless you had a theoretical argument why that one model was picked out. You can't.
Do we have a similar theoretical argument for what would you say?
Not yet. Not yet. I
Okay.
think in the case of the standard model, there are certainly some clues that it is quite unique. One of which is called anomaly cancellation. So for example, this is a very technical argument, but very beautiful argument, which makes the standard model work. And it only works for certain particles and forces and so on. Now, admittedly, there are many, many quantum field theories that are anomaly free. But you can see that this type of consistency requirement really picks out a very small subset of quantum field theories, among which is the standard model. And there's surprises about it. It predicts the quantization of charge. Why does an electron and a proton, why are the magnitudes of their charge the same? And why do quarks have exactly 1/3 or 2/3 those charge? This is explained by the anomaly cancellation, which is very technical but very beautiful theoretical argument. So I think
Well,
there are
well,
hints.
the particular charges are compatible with and yield anomaly cancellation.
Yes, yeah,
Is it a bit of a stretch to say that it explains
yeah.
them?
The quantization is explained. I mean, the quantization of electric charges among the standard model particles is explained. Now, the reason I mention this is that when I was, graduate student, grand unified theories were the big thing. And people realized that grand unified theories predict magnetic monopoles. And they got very excited about that because magnetic monopoles are wonderful things. They just don't happen to exist, but they would be wonderful if they did exist. And then Dirac had an old argument that if a monopole exists, it would explain the quantization of charge. So people are sort of very comfortable with one framework which explain this charge quantization. And I think many string theories are the same. They have charge quantization and they also have monopoles. But there is another explanation, which seems to work as well. And I would say that the anomaly cancellation mechanism is a clue that something very deep is going on in the standard model, which we can't yet, we don't yet fully understand. So I would say that, it's not that, my basic philosophy is we shouldn't be happy with our theories.
Mhm.
It's just not productive to be complacent and to say, we have this, and I'm afraid there's much too much complacency. People say, oh, quantum field theory is gorgeous and it's the ultimate theory of reality. And more or less any consistent quantum theory is fine. And I think the opposite is true. Again, if we go back to cosmology, um, the Big Bang.
Just
Yeah.
quickly, so on the particle physics front, then you would perhaps support students
Yes.
if they were saying things like, even though the standard model has done all this beautiful work in explaining all the data from the Large Hadron Collider and every other collider around the world, because of these issues, the flexibility and the framework, 90%, 90, I'm going to go down a different trajectory and see where I can go. That would be a direction that you presumably would support.
Absolutely. I
Yeah.
think we should. I mean, there are such young people. There are young
Yeah.
people who try to, they get very enamored with octonians, and they try to find ways in which octonians might eventually lead to the standard model. Um, and I think it's really important people do such investigations. I mean, it's very high risk because the standard model rests on, I don't know, 100 years of theoretical development. Um, so it is very high risk, but I think it's very important. The other,
Yeah, no, but I should say I remember a guy in graduate school, it just comes to mind,
yeah,
where he was developing his own alternative to quant, had these different Feynman rules and a whole different, and there were no divergences, so there was no renormalization. And now I don't think he got a job, right? So there is a push-pull in how far off the beaten track you go.
there are some people who are contrarian, and don't believe standard nostrums, who do extremely well, and are just brilliant theorists. I mean, I'm thinking of one person in particular. I won't say his name for fear of embarrassing him. He's in Italy, but so they're sort of standard arguments that um, in quantum field theory, you must get rid of states which have negative correspond to negative probabilities. This is a
The
huge,
ghosts.
huge issue. They're called
Yeah.
ghosts. And I remember Stephen Hawking giving a talk where he said the title was "Who is Afraid of Ghosts?" And he played on his computer, "Woo woo," you know. I'm not afraid of ghosts. So states which have negative probabilities are a no-go in quantum field theory.
And just for the audience, these are not negative probability amplitudes. These are
Right.
negative probabilities.
Exactly. So we don't really know how to make sense of them. Now, many theories, there are including string theory and the standard model type field theories called gauge theories, you do typically get negative norm states and then or negative probabilities, and then you discover you can get rid of them all. And in fact, my PhD advisor, David Olive, wrote the paper on the
Yeah.
superstring where they
Yep.
projected out all the negative probability states.
The GSO projection for those listening.
Exactly,
Yeah.
exactly. So it seems to be the way fundamental theories like that work is that for various reasons you work in a bigger space, which allows negative probabilities, but then uh, you know the physics only works in a subspace where there are only positive probabilities, and then you've got to work very hard to show that a state in the physical space only ever changes into a state in that physical space and never goes into a negative probability state. That's called a no-ghost theorem. Um, so that seems to be the way that certain very good theories work. Now, what I mentioned this particular Italian physicist because he is rather bravely re-examining theories which were discarded on the quantum field theories, which were discarded, sometimes because they involve more than two derivatives. So typically in physics equations, we don't have more than two time derivatives. Newton famously said F equals ma. The a is the second time derivative of the position. And so he formulated physics in terms of accelerations, forces drive accelerations. And this tradition of only having two time derivatives, has been extremely successful in physics. But it's quite easy to write down theories which have more than two. And these theories have some very attractive features. For example, if you try to write a theory of gravity which is insensitive to scale, Einstein's theory is not, but if you try to write down a theory of gravity which doesn't have a scale like the Planck length in it, that's called Weyl gravity after Hermann Weyl. This has higher derivatives, and it's more than two derivatives in its equations of motion. So some people, including this physicist I was mentioning, have figured out new ways to eliminate the negative probabilities in a very systematic, rigorous way that works to all orders in perturbation theory. I think it's very original and very deep. And I suspect that something like this is going to be useful in the future. We have some evidence for that in our own work. But I would say work like this is very important. It's just expanding our horizons to theories previously thought unviable, which may actually not only be viable, but be better um, than the best theories we currently have.
And so heading back to cosmology
Yeah.
with that,
Yeah.
philosophy, with that attitude, clearly when you approach something like inflation, you're going to be willing to embrace the possibilities of things that many other people would say, we've already got inflation. What are you doing?
Yes,
You know,
exactly.
you know.
Exactly. So people have become comfortable with considering theories which have a lot of free parameters, which don't make particularly clear predictions. Um, and often the arguments given in favor of these theories are very misleading. I mean, I hate to single someone out. I think very highly of Alan Guth, but he does give talks where he shows the cosmic microwave background temperature spectrum with bumps and wiggles. And he basically says, voila, inflation, predicts the bumps and wiggles. Absolutely not true. The bumps and wiggles are due to the oscillations in the plasma, which were understood by Chandrasekhar in the 1920s and earlier. They have nothing to do with inflation. So people have got into a mode where they, in order to make their work more exciting, more interesting, they kind of use spurious, arguments. And I think we've got to be ruthlessly self-critical and admit that the theory has an awful lot of baggage. Theory, it's not a theory, the framework has a lot of
Yeah.
baggage. And our job as theorists is to winnow that down and tried to, you know, I mean, we work in the greatest tradition in science. We have Maxwell, Newton, Einstein. The all of them had such clear theories that give incredibly precise predictions in realms they were never, originally intended to address. Einstein's theory predicts black holes, gravitational waves. It's just spectacular how it works. So, given that we're in this tradition, it's our duty to work to try to find similarly compelling and predictive theories.
But can I just ask you one? Because I certainly, um, I have no horse in the race, so to speak, but I have given talks on
Yeah,
inflation where maybe if you were in the audience, you would also recoil at what I'm saying. So I'm just, just to put all cards on the table here. So the thing about the fluctuation spectrum that certainly excited me as a student and still I find exciting is how you start, as you know, of course, but just for the audience, you start with a very simple field, a scalar field. You put it in a particular state, the lowest energy state, the vacuum state, and you run it through the machinery of quantum field theory in an inflationary universe. And the uncertainty principle, the oscillations of that field in the vacuum, when you spread them out in the sky, do give the seeds for the temperature variations that we see, in the microwave background radiation. Now, of course, there's a lot of astrophysics in there too, as you say. The baryon acoustic
exactly,
oscillation.
exactly.
But the fact that inflation
There is a
naturally,
mechanism. Yeah,
gives a mechanism
yeah.
that feels more than misleading. Do you know what
Well,
I mean? It feels
no, you're right, and it's very, very hard to come up with alternatives. And I think that would be the justification most people would give, and it's a reasonable justification. There being no alternative, we should believe, you know. But there is an alternative. Okay, so what started, and this is work with Latham Boyle, who was a faculty member with me at Perimeter Institute and moved to Edinburgh with me a year ago. So me and Latham, and I think it's something very hard to do on your own, is to try to go against such a strong orthodoxy as the inflationary orthodoxy. But we decided to take a fresh look. And what we essentially realized is that we could implement Hawking's idea for the no boundary proposal with a small tweak. And the small tweak was enough to make it viable. And so it's a highly predictive tweak. The tweak is that there's no inflation. Okay. You say, let's take the universe as we see it, full of radiation and matter, and literally just trace such a universe back to the Big Bang singularity. And we have to deal with the singularity. So we noticed some remarkable properties of the Big Bang singularity when it is dominated by radiation. So there's no inflation at all. Namely, there is a unique extension through the Big Bang out the other side. And this enabled us to propose a new boundary condition at the beginning of the universe, which we call the mirror hypothesis, or CPT, symmetric universe. So we figured out how to do this, how to calculate the measure Hawking had given us for such cosmologies. And to our amazement, it predicted spatially flat, homogeneous, isotropic universes.
When you say predicted, you mean it made it among the more likely?
Yeah, yeah,
Are we?
yes. So there are some provisos, provided so this gets technical, unfortunately, very quickly. But provided gravity allows a large number of states for the universe, in the limit as that number becomes large, you find the most likely universes are spatially flat. Okay, so we showed that. And furthermore, they're homogeneous and isotropic. They're the same everywhere in space, and they're the same in all directions. So we're very taken by that. We basically implemented Hawking's proposal in a more minimal framework with only radiation, which we know is there, and no inflation. And we got, in the first description, a universe just like ours, without any fluctuations, of course. So then we started thinking carefully and very naively. It's good to be naive. So we looked at the sky and we see the cosmic background fluctuations. If there was no inflation, where could they have come from? So let's be totally naive about it. Let's just say, they look like quantum fluctuations in a field. They have that statistical character. They're what's called Gaussian random noise. It's apparently very high accuracy. No deviations have been seen. And so there's an extremely pattern. It's just the probability of the temperature is a bell-shaped curve. It's a classic statistical distribution, the normal distribution. So that's what we see in the sky. So we just said, well, what kind of quantum field looks like that? And as soon as you ask the question, there's actually only one answer. And it's a kind of field which we call a dimension zero field, which has 4 derivatives in its equations. Okay, not 2. So if you just take the observations at face value, they are telling you there are fields in basic physics which have 4 derivatives. Such fields are dimensionless, and that immediately implies that their fluctuations in the vacuum have no scale. So it's scale invariant, like what we see in the sky.
So just so I can understand, so this field is a scalar field, like the inflaton field.
Exactly.
It doesn't have any indices on it.
Exactly.
Following. But you're saying that rather than having two derivative has four,
Right,
and then again for those following the details, because it's
right.
against the measure d4x, there's
Exactly.
there's no mass dimension to the field itself. So it's
Exactly right. Beautifully put. Beautifully put. So now,
and is that action, how much flexibility is there in that action? Now, if you got four derivatives, I would think.
almost nothing. The reason is that we wanted to describe the Big Bang singularity itself. Okay. And our whole picture rests on resolving the Big Bang singularity. Now, how do you resolve a singularity? It's crazy ambitious because in this picture of just radiation and a universe governed by Einstein's theory of gravity, when you trace the universe back, the entire space, all of space, shrinks to a point. Everything is at a single point with infinite density. It's indescribable. And that's what all the string theorists tell us. You're way too ambitious. You just can't describe such a thing. Well, that's not right, because if the matter has this special symmetry, which is called conformal symmetry, then actually saying the universe came out of a point is is working is sort of working in what we call a singular picture. It's the picture that's singular. It's not the physics that's singular. And we see this all over in physics. You can say, I mean, it's particularly a good example is black holes, where people thought they were singular on the horizon of a black hole, and then they realized that was just a coordinate artifact of using bad coordinates. And it's a similar thing here, that when you describe the size of the universe going to zero, if the material contents of the universe are insensitive to the size, then nobody can tell it went to zero. You can, what is called, blow up the singularity. It's a very well known technique in mathematics called a conformal blow up. And you can literally look at the singularity when it's blown up and study its properties.
And Penrose has been
Yeah,
saying something similar for a
very
long
long
time.
time. Even before inflation, he made a conjecture called the Weyl curvature hypothesis, which is a very beautiful conjecture. And he was trying to say, what is the difference between the initial singularity, the Big Bang singularity, and a final singularity, like the one you would encounter if you fell into a black hole? So he made this hypothesis that initial singularities have no Weyl curvature. What that means is that they can be blown up in a non-singular way into a non-singular space. You can literally, so imagine, use a microscope to look at this, tiny shaped object, but the light doesn't see the universe going to zero. The light behaves perfectly regularly. And so our discovery was that light and matter content, um, which is which has the same symmetry as light, that it doesn't care about the local scale of space, which is true of Dirac's theory of particles as well. That these theories actually do not detect a singularity. That
For massless
for
particles.
massless, for massive, it turns out the masses all become irrelevant at the singularity. So you can what's called change conformal frame into a description which is completely regular. So when we found that, we got very excited. We thought, oh, the Big Bang's not so dangerous as we thought. And as things have progressed, that's become more and more true. And so we were able to prove various things about the behavior of the space time in this singular limit.
So just so I fully understand, so in traditional course in general relativity, when
Yes,
one teaches about cosmology, you do find curvature invariants that do blow up at the Big Bang singularity. But you're saying that if the rest of your theory is scale invariant, is conformal invariant, that particular blowing up of a curvature invariant is irrelevant. Nothing will notice it because of the capacity to rescale everything.
exactly. Exactly. So now this is a very limited argument because it only applies to the matter. Okay. Gravity itself has a scale, which is the Planck scale, and gravity is not conformal invariant. So you can worry that the metric perturbations, gravitational waves, will see the singularity. Okay. Now, then something very beautiful happens, which is you say, okay, let's study the gravitational waves as they go back towards the singularity. What you discover is that exactly half of the modes are in fact regular at the Big Bang. They are smooth. They go right through it to the other side. The other half are singular. And so our proposal is it's this mirror hypothesis, is that the mirror implements what's called CPT symmetry. The pre-universe, the pre-bang universe, is the mirror image of the post-bang universe. And that forces you to exactly half of the modes. And those happen to be the regular modes. Okay, so it's literally the beginning. Enforcing this boundary condition of CPT symmetry at the beginning restricts you to regular metric perturbations at the beginning. And so even though gravity is not conformal, what happens is that you can restrict to regular conformal geometries. There's blow up the singularity, it's still regular, but at the price of throwing out half the modes. That's not a big price. That's very nice. And it turns out that the modes you keep are precisely the ones which give you the right wiggles in the cosmic microwave background. But you throw out the singular modes and you keep the regular
So
modes.
again, just so I fully understand, so there's two languages I gather which one could use here. One is this mirror language that there's sort of a pre-Big Bang part of the story, and when you put those together, it restricts the mode. Presumably, the other is you don't even have to talk about the pre-Big
Correct.
Bang. You just say there's a certain boundary condition
That's it.
at the bang itself, which restricts
Exactly.
the modes in the way that you're describing.
Exactly. Now, it's a very subtle thing because this, let me see yes, the way to, you see, there's a long-standing puzzle um, in general relativistic cosmology, which is that it's been known for a long time that there are solutions of the Einstein equations, which when you trace them back, become chaotic. As you go back towards the singularity, there's something called Mixmaster, which is a kind of machine. In the 60s, there was a famous thing for whizzing up egg yolks or whatever called a Mixmaster. And basically, as you follow the universe back, you get into this very random, chaotic motion. And so people were puzzled, what does that mean? That if we try to look at the singularity, we get this Mixmaster chaos. Our picture gets rid of all that because what we say is that the way we impose the boundary condition is not at the singularity itself. You see, that would be sort of the creator coming in and starting the universe. We do it in the opposite way. And I'm afraid this gets a little bit teleological. Okay, but I am coming to believe that some kind of teleological picture for quantum gravity is actually essential. And I'll explain why. So, how do you impose a boundary condition at the Big Bang where all of space is at a point and the density is infinite? Now, you can blow it up, but still, exactly how do you implement this in a sensible way? It's happening at the one place you have no idea how to really impose a boundary condition because the universe is so high, so dense, you know, um, that quantum gravity effects are everything. You really haven't got a clue what you're doing. So, how could you possibly get away with imposing with a mirror boundary condition at the singularity? The idea we have is the following: that you don't impose a boundary condition there. You impose the boundary condition by what's called the method of images. So just like when I solve light reflecting, so the light comes off my face, bounces off a mirror, and comes back to my eye. You could impose a boundary condition literally by thinking microscopically How does the electric field behave next to a mirror? There's a much neater way of doing it, which is to make a mirror image of yourself behind the mirror. So if I'm right-handed, I make a left-handed copy of myself, throw the mirror away, and just solve the equations from the mirror image to me, and that's what I would see. So it's a very well-known method in physics called the method of images. And so what we do is we say, okay, take a universe far away from the bang in the future, maybe to our future, take a exact copy of that universe, but under CPT, so particles go to antiparticles and space is inverted. Take a copy and ask, is there a classical solution which connects these two universes, the one before the bang and the one after it? And it turns out there is. If you make the pre-bang universe an identical copy of the post-bang one, both can be lumpy. And you ask, is there a classical solution which connects them, which is regular, which actually solves the equations all the way through? The answer is there is. There always is. And it's the demand that they be replicas is what halves the number of solutions. But they're all analytic. And all these chaotic mixmaster ones are just not solutions of the equations. They don't satisfy the Einstein equations. They shouldn't be taken seriously. So,
And what about in the quantum? So I gather your point is if we're
yeah,
sufficiently far from the singularity,
yeah,
that the quantum effects are suppressed, so this
exactly.
classical story is the one that I can focus my attention on.
Yeah,
But still, if I want to actually follow the dynamics from here to here, I've got to pass through this region. Now you say you can blow it up and use conformal symmetry, but I guess to what extent do you have a full quantum understanding of what's happening to the full gravitational story? Because that's been the
yeah.
conundrum, of course, for
No,
decades.
that's right. And we don't have a full. So as I mentioned, we can study the gravity classically, and then we study the matter in the universe quantum mechanically. So we do not have a full quantum picture. However, I would say that we know from other experience of quantum processes that asking a question of kind of exactly what happened in the middle of a quantum process is very seldom the right question to ask. You know,
But you want it to be well defined,
yeah,
right? I mean,
yes, but it won't be a classical picture. It won't
right.
be a single universe. It'll be, some superposition. A very nice analogy, and this is partly what inspires us, is in the creation of an electron positron pair. So that's a well-known physical process. If you turn on a very strong electric field, you literally drag an electron out of the vacuum along with its antiparticle, a positron, and the pair flies apart. Okay, so during the process of creation, you can't really say there's an electron or a positron. It's a fuzzy thing, and a classical electron will come out of it. And we think of the Big Bang as just such a process. There's a universe on one side, there's the anti-universe on the other side, and the two emerged together. The point of emergence is the one place you can't really talk about the geometry. Now, still, we would like to have a complete analysis of the geometry. There is a framework. It's called a path integral framework for gravity. It was invented by John Wheeler in the 50s and 60s. It's a very, very beautiful and compelling picture. What has not been done is enough technical development to understand, can I actually calculate things, to arbitrary precision? Now, one thing that should be clear in this picture is that the Big Bang singularity doesn't exist at a particular time. I've got this two-sided universe, but it's a geometry. It's flexible. It's a gravitational geometry. So the Big Bang, in some paths, the singularity will be nearer the future end, and some it'll be nearer the past end, and it will fluctuate. We should be able to calculate all that. We should be able to say how much uncertainty is there in the geometry around the time of the Big Bang. So that's very challenging, and I think it'll be exciting to try. We don't know that it won't work, but we don't know that it will either.
There was this proposal, I forget, you probably know of it better than I do, but maybe it's in the 60s or 70s. Somebody was trying to address, the Leibnizian question, why is there something rather than nothing?
Yeah,
And one of the ideas was maybe nothing is an unstable state
exactly.
and nothing sort of falls apart into something and an anti-something.
Beautiful.
It feels
Beautiful.
kind of similar to what you're.
Very, very, very similar, because you can say, what's the analog of the electric field? What made the positron electron? I think there's only one possible answer. It's the lambda. It's today's cosmological constant. That literally pulls space bigger and bigger, you know. So again, it's a little bit teleological because it's saying that the future influenced the past. That does seem to be the way the universe works. I mean, it contradicts our, classical pictures.
But do you literally mean that, or again, correct me if I'm wrong, is an alternative framing? There's a built-in coherence to the entirety of reality, which demands that the parts work together in ways. Or do you really want the future to affect the past?
No, it's more like what you said. The whole is coherent. And so I'm very influenced by Yakir Aharonov, who's one of the preeminent thinkers about quantum foundations. And he has a very interesting point, which is that so he asked the question, in what way is quantum mechanics different than classical mechanics? So in classical mechanics, if I prescribe the state of the system at one moment of time, so I tell you the coordinates and the velocities of every particle, then I just run the equations forward or backwards, and it's a machine, and you've got no more freedom. Quantum mechanics is different, and he calls it the two-time formalism. Because in quantum mechanics, I can completely specify the wave function at one time. And that's a complete prescription. That'll tell me everything about the state. And I can do it at a later time too. Because in quantum mechanics, you can only tell me the wave function, let's say, in the coordinate representation. You can't talk about the momentum and the coordinates. You have to use one or the other. This gives you the freedom to prescribe the final state as well as the initial state. And then you consider the amplitude, where I start from some initial state, evolve it forward, and overlap with the final state. So he calls this the two-time formalism in quantum mechanics. And it is a little bit teleological, because you're interested in physical processes happening in between, so this picture is called pre and post selection. I pre-select the wave function, I post-select the wave function, and I ask for whatever happened in between. And so now people are doing experiments, which, by the way, you describe brilliantly in one of your books. I think The Fabric of Reality. I mean, you spend 100 pages or something going through these experiments, which was gorgeous. So I think you understand this much better than I do. But yeah, this is a feature of quantum mechanics, is that it allows this pre and post selection. And when you think about lambda, the cosmological constant, is there ever going to be a good theory of it? Okay, and it's such a puzzle because it takes this crazy small positive value. Now, our calculations of the measure on the cosmology only work if lambda is positive. Okay, so basically, in technical terms, there is only an instanton. There's only a cosmological instanton if lambda is positive. And if it's positive, we can work out the entropy. And we find that the most probable universes have small positive lambda. It's actually, it's not original to us. Hawking wrote papers about this, Sidney Coleman.
Yeah, Sidney Coleman, yeah.
Exactly. So we've just made it the same calculations, but in a realistic universe, which has radiation and matter.
Yeah, I can't help but it happens to be on my desk right here. I've got,
Yeah.
reading is, I never tire of it. So
the best ever book on quantum field theory.
yes,
Absolutely. It's just a treasure trove. So
yeah.
yeah, actually, I can't help mentioning, I was very fortunate as a postdoc. I went to Harvard to give a talk, and Sidney Coleman's in the audience. And I was talking about cosmic strings. Uh,
I'm almost positive I was at that talk
were
because I
you?
remember you giving a talk on cosmic strings
Yes,
in Jefferson 351 or
correct,
something like, or
correct. You
yeah,
know, and the great Sidney Coleman asked me a question, and I was just blown away. And he really wanted to know what are these solutions. And so, yeah, he was such an amazing person. And yeah, so this is why I'm still in physics. You know, the one thing being in physics does, you get to meet the most amazing people.
No, I second that. I second that. But can I drill down on entropy for a
Sure,
little bit, which I
please.
think will allow us to illuminate the ideas that you're proposing, perhaps even from another angle. So we may cover similar ground, but just from a different perspective. So you mentioned Penrose, and he had this beautiful drawing and of a like somebody like a I don't know God figure or something like in the space of all universes, like picking out one, which is ours. Basically, trying to say there's this puzzle of why ours among all possibilities that can be out there. And entropy is a way of quantifying that, as we discussed a little bit earlier, because high entropy means there are many ways of realizing that configuration. So it's in some sense easy for the universe to realize that state, whereas low entropy, special, harder. You have to work harder for that state to be realized. And so you mentioned earlier that in some sense, inflation makes the puzzle worse, of what Roger was pointing out. Much to the chagrin, I could sort of feel the tension in the room when Roger would make this point during a talk on inflation. But it's sort of obvious. If the second law says that entropy increases toward the future, then the further back you go, the lower the entropy is going to be, the rarer it's going to be. And inflation kind of has a whole prehistory before the bang, if you will.
Right,
And so the entropy just gets smaller and smaller. The conditions are more and more special for inflation to happen.
exactly.
How does your approach address that entropy issue?
Right. So what? So Stephen Hawking, of course, is the founder of this whole field of with Bekenstein, but Hawking had the mathematical framework. So Hawking studied all this in the context of black holes. So the first discovery, I guess he made, was that black hole spacetimes, which are deeply paradoxical because they have a horizon, they have a singularity inside them, and so on. But what Hawking and Gibbons realized was that black hole spacetimes, if you make time imaginary instead of real, are beautiful regular geometries. And they are periodic in imaginary time. So now, why imaginary time? Well, imaginary time is what you use if you want to describe a statistical ensemble. So in
And just so people know, when you say imaginary time, it's not,
no,
square root of -1, I times
right,
t. Really the imaginary numbers.
the
Yeah. Okay.
imaginary numbers. So
Yeah.
so basically in quantum mechanics, you have complex numbers play a central role. And the imaginary number comes into Schrodinger's equation, and it tells you how the phase of the wave function evolves, the complex phase. But in statistical mechanics, there are only probabilities. And here you have an exponential, which is called the Boltzmann factor, e to the minus energy over temperature. And the point of this mapping is that the one thing goes into the other. The time evolution operator in Schrodinger quantum mechanics goes over into Boltzmann's. So it's this incredibly powerful mathematical trick which relates quantum mechanics to statistical physics. So Hawking was very taken with this, and he realized that black holes are actually uh, are periodic in imaginary time. The Hawking temperature, what is it? It's just the period in imaginary time. That's all it is. So if you tell me the mass of the black hole, I just go and look in imaginary time, and I'll find that the space-time is periodic, and the period is the Hawking temperature. What is the entropy? So the entropy is something equally fundamental. You take Einstein's action. It's like the variational principle that gives the Einstein equations, and just calculate that action for the metric. where I integrate over imaginary time. And that's the entropy. So Hawking came up with this kind of one-line argument that tells you how many microstates correspond to a black hole. And people have been, puzzling over this for decades since, trying to make sense of this crazy formula that tells you how many ways you can make a black hole in such an elegant and minimal calculation. And I think they've, up till now, failed to really get to the bottom. I mean, there's a lot of evidence it's correct, and in less than 4 dimensions, people know how to really show it's correct. But in 4 dimensions, it's still a little bit elusive how to really prove that formula.
Although string theory has given some insights, we don't have to go down that trajectory.
Absolutely. No, string theory has been more or less the only route available to sort of as a as a laboratory, as a mathematical laboratory, to examine the validity of Hawking's reasoning. And actually, amazingly, string theory, has been in agreement with these arguments, which is a plus for string theory and also for Hawking's arguments. So what we did is so if you count how many states there are in a black hole, you see again it's a little bit teleological, in the sense you've got to go to imaginary time. There's no real notion of causality in imaginary time. It is what it is. It's a universe without time. It's a black hole without time. And in that picture, you can count how many states there are for a black hole. So our contribution was to realize that exactly the same arguments work for cosmology. That if you have a cosmology with radiation, matter, a cosmological constant, and space curvature, arbitrary, all of those things arbitrary, you can find the Euclidean or imaginary time solutions. So we found all of them, and just calculate the action, and that gives you the entropy. So we have a formula for how many states there are for a universe with various parameters. And this formula says that there are more states for universes that are spatially flat, and there are more states if they have a small positive cosmological constant.
And how though do I intuitively, like, I've not gone through those
Yeah,
calculations.
they're very
Your
easy.
description of them
Very,
makes them very intriguing. So
yeah,
after the conversation, I think I'm inspired to go actually read the papers, and maybe we could talk again at that point. But is there an explanation, perhaps at an intuitive level, for why Roger's argument? Roger would always say that the high entropy state near the Big Bang should have been a bath of black holes. I mean, the gravitational degrees of freedom should have been excited to a state where you'd have this, because black holes, the highest entropy. So apparently, you're not finding
no,
that
we're not
state.
not finding that at all.
And can you give a sense of
Yeah.
why?
Yes, it's very simple. It's for the same reason that when you solve the equations for a soap bubble, it's smooth and round. You don't have to put that in. That's the that's
Well,
the
that's like surface tension and
yeah,
I mean,
yeah.
it feels a little different.
No,
No?
no, it's quite similar. I mean, what is
Okay.
Einstein's theory is a geometrical theory. So it has a lambda, it has radiation, which makes pressure. And you literally, when you solve the equations properly, but as I say, it is teleological because it's all in imaginary time. You're solving these imaginary time equations in which the cosmological constant plays a dominant role because it's there. So the size of this, what's called gravitational instanton, it's this imaginary time geometry, the size is controlled by the cosmological constant. Okay, so so you then say, okay, well, that's a sort of typical universe is big, and the cosmological constant controls its size. In fact, the four volume of the instanton or these imaginary time solutions, the four volume is directly controlled by lambda. If you think of how the cosmological constant comes into physics, it is precisely the multiple of the four volume in the action. That's what it is. So we think of it, when you do statistical physics, you always have to fix something and vary something else. And so typically, microscopically, you can think of fixing the total energy in a box. And then I ask, what's a typical state with given energy? For gravity, you'd say, what's a typical state with given four volume, right? Now, that's hard to frame because it just uh, what's called the microcanonical ensemble in statistical physics usually harder to calculate than. So the way around it is you introduce a temperature. You sum over everything, but you put the Boltzmann weight, and the temperature you dial to control the total energy. In the same way, we sum over four volume in our calculation, but we put in the lambda to control the four volume. Okay, so it's really very similar to what you do in usual statistical physics, but the lambda is a control parameter which you use. And in that way, I think it becomes quite plausible that, I mean, it's sort of pushing the question into another one. So instead of explaining the value of lambda, why it's so tiny and positive, the question now becomes, why is the four volume of the universe so big? To the extent it's big, the lambda is small. Okay.
Right. And so when I try to go back from the imaginary time formalism to a real time interpretation,
Yes.
would this be saying that the more likely late time universe
Yes.
is large and small lambda? But can you
Yeah.
tell me anything
Yeah.
about the dynamics?
Absolutely. Yes. Because it turns out these solutions are analytic in time. So if you know what they are in imaginary time, you can just go to real time and see what they look like. So you translate it directly into real time. But
And
with this, apparently teleological thing that because the universe knows its own entirety in imaginary time, um, the future is in a certain sense predetermined.
right. And so, can you help me understand the dynamics in an entropic framework? Because normally, what I think about is we want early time to have low entropy so that the universe can unwind and have the opportunity to go to high entropy, as it evolves. Do you have a similar low entropy to high entropy? No. So how do you disabuse me of this need to have a low entropy start so that there's an opportunity for high entropy to
Very
follow?
good, very good. So, entropy, we usually think of entropy in thermal equilibrium. Imagine a box of atoms or whatever at some temperature, and we say, how much entropy in the atoms? Um, when we deal with gravity, it's inherently non equilibrium. Gravitating systems are almost never in equilibrium. So, and this is even classical gravity. If you have a clump of stars or planets orbiting each other, they cannot achieve thermal equilibrium. Why? Because occasionally they will kick one out of the clump just by three body interactions, and the clump becomes more tightly bound. And as it kicks the high energy particles out, the whole thing becomes more and more tightly bound, and eventually it just sinks down and collapses to arbitrarily small size and eventually makes a black hole. So, gravitating systems, because gravity is attractive always, never have thermal equilibrium. Even for a black hole, if you Hawking showed black holes have a temperature, so they radiate. So if I have a black hole sitting there in flat space, it will eventually go away and just go into radiation. So you can try to make it in equilibrium by having it in a reflecting box where the radiation comes back into the black hole. But no one really knows how to make a box in gravity, and so even that doesn't really work. So certainly the universe is not in equilibrium. Okay. So when you talk about entropy, you've got to talk about the entropy of a non-equilibrium system. Now that's fine because entropy is a concept which relates to information. Information is the fundamental thing. It's not restricted to equilibrium at all. If I tell you, somebody tells me I traveled from London to Edinburgh yesterday. I can say, well, what was the most plausible route? So I would take all possible routes by road or train, and I'll weight them accordingly. And that's not an equilibrium system, but you can perfectly well discuss probability of different paths. And in fact, the inventor of the information theory approach to statistical physics, a guy called E.T. Jaynes, went on to invent a concept called maximum caliber, where caliber was the generalization of entropy. And caliber was
I've
the
never heard of this, by the way. I've never
yeah,
heard
no,
of Cal.
it's experiencing a revival in areas like mathematical biology, where you have predator prey models and time evolving systems, and people are trying to figure out what's probable and improbable in evolution, let's say. um, uh, and so caliber is really just the entropy of a path. And we know if you do a random walk, certain paths are more likely than certain collections of paths more likely than others. So when you do gravity, you've got to generalize your notion of entropy to the entropy of a path. And that means there's a past and a future, and I calculate the likelihood of all possible routes between one and the other. So you just shouldn't talk about the entropy of the beginning and does it increase. The entropy at a fixed time. Gravitational entropy doesn't exist at a fixed time. It exists for the whole of time. And so, in fact, mathematically, when we calculate this gravitational entropy, you do an integral over imaginary time, and you can show that if you translate that integral in real time, it's invariant. So the gravitational entropy doesn't depend on time at all. It's just the number associated with the geometry. It's independent of time. So again, this makes it a bit teleological. We have to get our heads around this. What I have not seen and really needs to be done is to say, in such a framework, would somebody living in the universe have any advanced knowledge? Okay. And I think it's an interesting question. And I don't know the answer yet, but I think it's perfectly addressable. Uh,
Now, when you say that the higher probability are these um, geometries with a small cosmological constant, small is an interesting adjective because there's small, there's very small, there's really tiny. Is there anything that points toward the actual value of the dark energy cosmological constant that
yeah,
fits observations?
yeah. So the way it works is that the so it relates to the what's called the total dimension of the Hilbert space. Okay. So gravity again is very unusual in that there are reasons to believe that the space of possible states in a gravitating system is finite. This is not the same as quantum field theory. Quantum field theory, if I pump in more energy, I have access to more states and I can go to infinity. But in gravity, it is believed that the Hilbert space is finite dimensional. There's only a finite number of states. So there is a number that comes in there, the dimension of Hilbert space. And it turns out that the lambda we see, the most probable lambda we see, is the log. The most probable lambda we see is yes, the inverse of lambda is the log of the dimension of the Hilbert space.
So the dimension of the universe is like 10 to the 10 to the 120 or something like that.
Yes, exactly. And the lambda is the inverse of the log, so it would be 10 to the minus 120. Exactly.
Right.
Now, yeah. So that's basically how it works. That the lambda.
But can you calculate? And I mean, obviously, one of the big conundrums as well in quantum field theory, even in string theory too, frankly, has been to have a first principles calculation of this bizarre number, which decimal point 120 zeros and a one in essence. Have you made any progress in
No,
calculating it?
no. So we just put it in as whatever it is. So another way of saying it is that we're only using Einstein gravity to calculate all these things. Einstein gravity is a continuum theory. You can dial the parameters to whatever you want. If we dial the um, if we dial the Hilbert space dimension, so there's no concept of Hilbert space dimension in Einstein's classical theory of gravity. So we just have to input it and then say lambda cannot be smaller than a certain amount because there's just not enough states in the Hilbert space. So it's using a low energy approximate theory to try to learn something about microscopic theory. So it's very, very primitive stage. And I think string theory, to its enormous credit, does give you a microscopic theory and you can count the states. And where people have done that, I mean, Ashok Sen has done some amazing recent calculations, again, giving evidence that, for very precise correspondence between Hawking-like calculations and string theory allows you to go beyond the Hawking-like calculations and compute the next corrections, which is so that's very important. We're not there yet. I just want to make one comment. So it comes back to these dimensionless fields. We need them to explain the fluctuations we see in the sky. Those dimension zero fields are the exact analog of the string worldsheet coordinates in 2 dimensions. And you can exponentiate them to get vertex operators, which are fundamental objects in string theory. So if what we're saying is right, there are 4-dimensional vertex operators, and there's a whole 4-dimensional version of string theory, which is waiting to be understood.
Or string theory architecture, right? Not
Correct.
yeah, yeah.
Very, very analogous to string theory. All the principles which were so effective in string theory, like uh, this conformal symmetry in string theory, is absolutely fundamental in 2 dimensions. It's the driving principle behind the theory. It's how you resolve singularities, like when strings split and join. So we're just saying exactly the same needs to be developed in 4 dimensions. And the the hints from observation are that something like this is going on, because when you look at the CMB fluctuations, that's what you see. You see scale invariant fluctuations. If any, this is just telling us that the universe has conformal symmetry built into it.
So if we, and I mean broadly defined
Yeah,
if we detect primordial gravitational waves, presumably that would be a point where you'd give up.
absolutely. Yeah,
Okay,
give up tomorrow.
fine.
If they are discovered, I will be the first to acknowledge that inflation was right. Um, I'm betting against that, um, mainly out of hope that there is a beautiful theory. And I think that where we've been forced to with inflation so far is not very beautiful. Namely, the simplest versions of inflation, which had a quadratic potential or quartic, 5 to the 4th potential, those are now ruled out because they predict too many gravitational waves. The sort of most elegant versions of inflation which have survived, the one parameter theories, one of them is called a Starobinsky model, which is a cute idea. Again, it's to do with conformal symmetry, what's called a conformal anomaly. And I think it's conceptually flawed, and actually even Starobinsky doesn't really defend the conceptual foundations anymore. But it does make a prediction, and it predicts the gravitational wave background would be about 10 times smaller than the current upper limit. Current upper limit is about 3% of the CMB anisotropy due to gravitational waves, and they predict about 0.3%. So, fortunately, by the end of this decade, it is forecast from the Simons Observatory and others that the limit will go below then to 0.1%. And if Starobinsky is ruled out, then I really think there's no hope for an elegant inflationary model. There's another version called Higgs inflation, but again, one can have many misgivings about it, but predicts a value in the similar ballpark.
But don't you feel it likely, just historically speaking,
Yeah,
that some clever theorist will come up with some elegant version of inflation that perhaps isn't in the market yet that would be compatible with the failure to see gravitational
it's
waves
perfectly
at that
possible.
level?
It's perfectly possible. I what I would be most convinced by is if somebody found a good way to implement Hawking's original proposal in inflation with string theory, preferably. Okay, and you know, it just worked. That would be extraordinary, and I would believe. So, I went into studying Hawking's proposal enthusiastically, um, and I was perfectly ready to accept that this is the right explanation if it worked. It just didn't work. We haven't found the right way to make it work. Our theory is a sort of twisted version of Hawking's, where we add this mirror, and this. I mean, I like it because the CPT symmetry is very fundamental. But do I believe it? Not really. I mean, I don't believe anything until it's compelling, and I don't think anyone else should either.
No, I totally agree with that.
Yeah.
But if we fail to see the primordial gravitational waves, the B mode print on the CMB, Paul Steinhardt will likely interpret that A as evidence against inflation and B as evidence for the cyclic ideas that you and he developed prior to the work that we spent most of our time talking about here today. Presumably, you no longer you're not convinced of inflation and you have these real reasons against it. Where do you stand on the cyclic models?
So Penrose also is advocating cyclic
Yeah,
models in
yeah.
a different way, and I have tried to talk him out of it. I
Good
mean,
luck.
we
Good
we
luck.
we meet very regularly. I mean, Penrose is just the most amazing human being. I mean, he's just extraordinary, generous, you know, brilliant in the nth degree. So it's a huge honor ever to talk to him. But yeah, I've tried to talk him out of cyclic because I think partly he took it up because of Steinhardt and me and our work. But the reason I became disenamored with cyclic is that, if that's a word, is that it became just as contrived, if not more contrived, than inflation. In that, to explain what we see in the sky, we had to dial potentials and parameters and make assumptions about initial conditions. Has a worse problem in that you've got to describe the passage through the singularity. Now, I would have liked it if there was somehow a compelling story about that passage. And initially, Paul and I hoped that the collision of brains in M theory was such a compelling picture. M theory, there are these sheets which just look like three-dimensional universes, and they can collide. And that sounded very nice as a mechanism for the Big Bang. But the more we thought about it, the more difficult it seemed to describe that event. Um, and so, yeah, it all became very artificial and ad hoc. So now Paul and Anna Idjus have some models where they claim they can get the universe to bounce and avoid a singularity altogether, but it's at a high price. It's a price that you introduce more and more parameters and artificiality. Whereas I say, what motivates me is the observations are so simple. I kind of think now, what I'm excited about, that doesn't mean it's true, but what I'm excited about is these dimensionless scalar fields. we basically adopted several tricks from string theory, technically known as cancelling conformal anomalies. And then we found we could predict the amplitude and the spectrum of what we see in the sky using only the standard model. Okay. And it turns out that the tilt is exactly predicted in terms of the strong coupling constant extrapolated to the Planck scale. And the amplitude is also predicted. And
Let me just see if I understand. Just so I understand. So you're saying you take the standard model,
yeah,
you augment it by these
dimensionless fields.
dimensionless scalar fields.
Right.
You require that all anomalies
Cancel.
cancel.
Exactly. What happens is, so there's a very amazing, now this is, I should emphasize, this is very simplistic calculation. It is the lowest order, no interactions, free fields. So very elementary calculation.
So you want just counting the number of degrees of freedom.
Exactly right. Exactly
Right.
right. So something totally remarkable happened. And by the way, some mathematicians have recently confirmed our calculations. Very exciting, using twister methods. But and this is not published yet. But there's a Kevin Costello who's at Perimeter Institute. So I shouldn't spill the beans. But what? So
Or we can hold this until.
no, it's okay. It's okay. It's okay. It's fine. So you introduce these funny scalar fields with four derivatives. Then we noticed that people in the past had calculated their contribution to the conformal anomalies. Now, the standard model has gauge fields and fermions and the Higgs boson. They all contribute positively to these anomalies. You can't cancel them. It just turns out that these scalar fields contribute negatively. The four derivative guys contribute negatively to both the conformal anomalies. So you get a bunch of integers. For n of these scalar fields, you have a sum of integers, the standard model plus these guys, and you demand these sums vanish. Then we also impose the condition that the vacuum energy vanish at lowest order, because we want to couple gravity to these fields. You know, the vacuum energy is this awful thing that you get infinite vacuum energy. You don't know how to couple fields to it. You certainly can't do perturbation theory. So we impose that three sums of integers vanish. The first consequence was that there is no fundamental Higgs. Okay, which sounds like
But in principle, there may not even be any integer solution to this
exactly,
simultaneous.
exactly.
Right?
It's a bit of a miracle as any solution.
Okay.
Because the coefficients of these integers are typically fractions.
Because you got fractional degrees of freedom coming from the fermions and things like that.
Exactly. Yeah, okay. So it's a very limited calculation. We take a curved spacetime. We don't include gravity as a degree of freedom. It's a curved spacetime. We put the standard model on it. We put these dimensionless fields on it, and we add up the anomalies in conformal symmetry. So if you rescale the background locally, physics ought not to change, but typically it does because of these anomalies. So you get two sums of integers from that should vanish. And thirdly, you get the vacuum energy. So in the standard model, the net vacuum energy is minus infinity from the fermions, so more fermions and bosons. We set these three sums of integers to zero. By the way, the dimensionless fields contribute positively, so to the vacuum energy, but negatively to the anomalies. So cancellation is now possible. You find it cancels only if there's no fundamental Higgs boson. Okay, so that must be made from the dimensionless fields. And by the way, there's a good route to doing that. Okay, so
you mean through a vertex operator, through exponentiating the
yes, exactly. Okay. Take a dimensionless field which has logarithmic correlations, exponentiate it, and you get power law correlation.
Right.
So there is a chance of explaining the Higgs, and I think a very good chance. And by the way, this would solve the hierarchy problem, because this particular theory with these dimensionless scalars is what's called asymptotically free. It turns so the coupling gets strong as you decrease the energy. So it could get strong at the electroweak scale, and you can get a Higgs condensating, and there would be no hierarchy problem in that picture. So these three sums of integers should vanish. First thing is the Higgs can't be fundamental. That sounds like a bad thing. It's not a doesn't agree with the standard model physics. The second thing is you predict that there are, let me think, yes, the number of fermions is 4 times the number of gauge bosons. The standard model, that's 12. There have to be 48. Now, 16 fermions make up one generation of particles, as you know from SO10.
Ah, so you've explained 3 generations
We
for
have.
us for
We have.
this.
So
That's great.
this gives 3 generations.
Wow.
As far as I know, it's the simplest explanation. Finally, you say, how many of these dimensionless scalars do you have? And it turns out there are 36. There have to be 36 for these numbers to. So it's kind of unique. The solution is, there are ways to make it non-unique, but it's more or less unique. So SU5 doesn't work, SO10 doesn't work. Standard model.
Does 36 bother you from the simplicity standpoint, or it is what it is?
No, it's a clue.
Okay.
36 happens to be the dimension of the group SP8. SP8 is very special. It's the group of symmetries on 4-dimensional phase space, x mu and p mu. It includes twistor theory. It's like a mega twistor theory. Okay. And SP8 is very unusual. It also has a compact version. It's a non-compact group, which normally is scary because it leads to ghosts and things. Has a compact version which is actually the unitary group U4, where the elements of the matrices are quaternions, U4 comma Q. That is SP8.
Okay. I'll trust you on that. I don't know that fact.
It contains a standard model.
I see.
So these are all just numerological clues
Right.
that there may be a different way of getting the standard model than has been thought of so far with grand unified theories.
So you're saying some symmetry breaking on some symplectic group or
Exactly.
something?
Yeah, exactly. Now, it's got to be a very subtle symmetry because it would combine space-time symmetries with internal symmetries. And there's a no-go theorem that you can't do that. There's a theorem called Coleman-Mandular by Sidney Coleman. But what this is hinting at is a way around that theorem. And if so, that would be a unification which combines space-time, which actually is one.
But of course, supersymmetry is also sort of one way around this, but it's a bit
Exactly.
you know.
So this is a different way to achieve the same ends. And I should say all of this is extremely preliminary. We're just taking baby steps. I mean, building a 4-dimensional version of string theory using the same ideas is obviously a Herculean task. Okay. So I've got some great students and they're working very hard, but it's tough. So we have a new result, which is a no-ghost theorem that we can show that
On those dimension zero fields,
yeah. So we've shown that. We've shown they're asymptotically free, which is a good feature.
And do you have to do some sort of projection to
Yeah.
get rid of you do this too? So
Exactly.
like we discussed earlier, some GSO type.
Exactly.
Okay.
You have to do a projection. Now, these dimensionless fields are really funny things because they've been floating around in the literature since the 1950s. Werner Heisenberg started off thinking about this, and it turns out they realize a dream of Dirac. So Dirac noticed that the conformal group in 4 dimensions, SO42, it's non-compact. It has an infinite dimensional representation, which includes every massless integer spin field once and only once. Okay, so it would include photons, gravitons, and all spins. So it's sort of progenitor of string theory, really, on purely group theoretic grounds.
Yeah.
And then later, two mathematicians called Flato and Fronsdal showed that dimensionless fields implement Dirac's singleton, his idea. They do provide an explicit representation. And this is all deeply related to conformal symmetry, which is also deeply related to twistors. So, all these ideas are sort of circling around the same concepts. I wasn't aware any of this existed until, recently.
I've learned a lot in this conversation. I've known of course, dimension zero fields from string theory, but I've
Yeah,
never thought about them in a space-time context in the way
yeah.
that you're
I think
describing. So
everybody just rejected them because well, for two reasons. One, it's been known ever since 1820 or 30 that theories with more than two time derivatives, if you have a Lagrangian which where the field equations involve more than two time derivatives, the Hamiltonian is unbounded below. So that's called the Ostrogradsky problem. So there's a danger in these theories that these funny fields can soak up large amounts of they can acquire large amounts of negative energy while everything else gets arbitrarily positive energy. The whole thing is unstable.
which is why we talk about acceleration and not jerk, right? I
Right.
mean, most classical physics classes don't talk about jerk, but I think jerk is the
Exactly.
derivative of acceleration. I think that's the word. If I have it, if
Yeah,
someone can
that's
correct me in the
correct. No,
comments.
that's exactly right. We never talk about jerk. Yeah, that's right.
Right, right. But in
So
principle, you could. I mean, but mathematically, it's awkward.
that's right. So, but the important point about that statement, it's completely classical. Okay,
Yeah.
the classical theory is an unbounded energy. Now we know of an example where a classical theory with unbounded negative energy entered physics, and that's the fermion, Dirac's theory of fermion. Yes, they have classically unbounded negative energy. You quantize them carefully as fermions, and all those negative energy states become inaccessible because you filled them all and used the Pauli exclusion principle. So there was a case of rescuing a theory which is classically, unviable. And so can you do the same with these dimensionless fields? So it turns out that when you quantize the dimensionless fields, indeed, there's basically two options. Either have all probabilities positive and my energy is unbounded below, or I can have the energies all positive and some of the probabilities positive and some negative. So that's the route we choose to go. We keep so the energies of every state is positive, and now we've got the problem of negative probabilities. So now we must do the projection. But what we've shown is if you do both of those things, the theory is fine. So I think sort of trawling the old literature for theories which were apparently, disastrous and rescuing them is not a crazy thing to do.
Yeah. No, it sounds very promising.
Yeah,
So let me just end with two things, Neil, if you have
sure,
another couple
sure.
minutes. We've pretty much covered, but just, well, first off, as a quick summary, because we've gone through a lot of things, I gather the summary is you have this new proposal of this mirror universe scenario or this, CPT invariant overall, cosmology, where you claim, and I'll have to read the papers, but I'm sure what you're describing is accurate. You claim that you can make sense of the Big Bang singularity through this conformal symmetry. You have a natural explanation of fluctuations in the CMB, which, as you say, is usually used as here's why inflation is correct, but alternatives are really potent. You introduce this to me and perhaps many of my colleagues this somewhat exotic idea in four dimensions of a dimension zero, a scalar field, which you say you can cancel all chiral anomalies, Weyl anomalies from this, and it fixes the number of fields to be 36. And if I understood correctly, also fixes the number of generations to be 3 for the integer numerology to have a solution for it to all work out. Um, and no inflation in this story whatsoever. So, are there other claims to fame, or those the summary of the?
There's one more claim, which is, in fact, what got us started on this, and haven't talked about it at all. If you were to ask me, what is the evidence for physics beyond the Standard Model, then until 2018, I would have said the dark matter. We seem to need another particle, a WIMP or an axion or something. In 2018, so Latham, Boyle, and I were thinking about this remarkable fact that the Big Bang singularity allows you to extend across it to this mirror universe before. And we thought, might we be able to rescue a certain candidate from a candidate for the dark matter, which has always been overlooked? And that candidate is sort of blindingly obvious with hindsight. It's one of the right-handed neutrinos. So in the Standard Model, there's a sort of puzzle. It's sometimes called the minimal Standard Model, only has left-handed neutrinos, whereas all other particles have both left and right. That model is ruled out anyway because the neutrinos would have to be exactly massless. So it was known since the 70s that if you include a right-handed neutrino, so now every particle has both left and right, then there's a very nice mechanism whereby the right-handed neutrinos endow the left-handed ones with tiny masses. That's called the seesaw mechanism. So the right-handed guys are neutral to all charges in the Standard Model. They don't interact with the force fields. They do interact with the Higgs and the left-handed neutrinos. So as a left-handed neutrino travels along, it sees the Higgs in the vacuum, transmutes into a right-handed guy for a short time, and then under the influence of the Higgs in the vacuum, goes back to being left. And that gives it little mass, this mixing process. So that's called a seesaw. And the heavier you make the right-handed guys, the lighter the light neutrinos become. So neutrinos are observed to have small masses, at least small mass differences.
Mass differences.
Yeah,
Yeah,
that's all that's known is two mass differences. What is not known is the absolute scale of the neutrino, the three light neutrino masses. So what we realized with our new picture, is that we could calculate that if one of the right-handed guys was stable, so imagine it's stable, that means it doesn't couple to anything else in the Standard Model. It just sits there, only couples to gravity. It's very obvious as a dark matter candidate because it has no interaction.
but presumably that makes the left-handed guy massless.
Exactly right. Exactly.
Yeah.
You got it in one. So that's the prediction. So it turns out we were.
Wait, so your prediction is that one of the
It's
neutrinos, the
massless.
Standard Model, is actually massless?
Exactly. If that is the case, and that's now being tested in galaxy surveys, remarkably, the most precise way we have of measuring neutrino masses.
Oh, because you're sensitive to the sum of the masses,
Yeah,
I guess.
yes.
Yeah, okay.
So we know
They
that.
got the sum and the differences.
Yes, we know the two differences. So we
Right.
predict the sum. Okay. And amazingly, galaxy surveys in the next 3 to 4 years will be precise enough in measuring how galaxies clump to tell the difference between a theory where the lightest neutrino is massive or massless at some precision. I mean, it will.
But presumably it could set an upper limit
Yeah,
to that mass, and then
yeah.
you'd be okay.
Yes. So currently, there are actually two possibilities. You know, we know these two mass differences, and either it's the highest two masses with the small mass difference, or it's the lowest two with the small mass difference. So there's the normal hierarchy where the masses. The other way. This is the normal hierarchy where the two lightest ones have the small mass difference.
Oh, it could be the inverted
The
hierarchy.
inverted hierarchy, where the two heavy ones have a small mass difference.
Small difference.
Yeah,
right.
so already the measurements are strongly disfavoring the inverted hierarchy. So that's amazing that you can do that from galaxy surveys. They now claim that they should have enough accuracy to measure the sum of the neutrino masses as compared with our prediction, which is that it's the minimum possible sum. And they will have that accuracy to about 5 sigma within 2 or 3 years. So if the lightest neutrino is massless, that will be evidence that one of the right-handed neutrinos is stable.
How heavy would it have to be the dark matter?
5 times 10 to the 8 GeV.
500 million times per. I see.
Yeah. So it's not, it's halfway to the Planck scale.
Right. Right.
So we in this picture are.
And how would you do direct detection? How
Oh,
would you look?
it's so difficult. So
Okay.
difficult. You can predict the rate of a rare process called neutrinoless double beta decay. But unfortunately, our prediction is that that rate should be the minimum possible allowed by the standard model. So they are now building the experiment. It will take at least 10 years to get it working properly, probably another couple of decades to get the accuracy to test our prediction. So it is testable, but it's very difficult. I think most promising would be, I mean, it's very futuristic, but if this really is the dark matter, there would be gravitationally bound clumps of 5 times 10 to the 8 GeV particles. And they would be on all scales, down to millimeter size clumps flying around the universe. And you would want to put a super sensitive gravity detector in space and look at the shot noise of these clumps flying
Wow.
past. Which is a minuscule effect, but we've thought about it, somewhat, and it's not impossible. So there are other very exciting directions about probing what really happened at the Big Bang singularity. If inflation happened, then when you looked in the gravitational wave spectrum, you know, you would okay, I have to think carefully. Yeah, if you looked using gravitational waves, gravitational waves should be produced thermally, just in the same way as the cosmic microwave background was produced. That you'd have interactions of photons and particles, and they'd emit gravitational waves. There should be a background going all the way back to the Planck time. So the universe should be full of relic gravitational waves. And amazingly, people are now designing detectors that one day may be able to measure them. There's a big workshop held at CERN last Christmas, all about this. So that's really exciting. Now, if inflation happened, those high frequency gravitational waves wouldn't be there. They would have been wiped out by the inflation, and then you'd see a signal from reheating at a much lower temperature. So only the hot plasma would be released, then it would release gravitational waves at that temperature, much lower than the Planck. So yeah, there are literally the Big Bang is a microscope. We can use it to tell the difference between these theories. So we've all got to stay healthy and live as long as possible because amazing things are coming.
Yeah, we just have to make sure we as a civilization stay healthy too, which in the
Oh,
current era is a whole different story.
that is the most
Yeah,
important question for
yeah,
sure.
absolutely.
Yeah.
So, look, this is a fascinating conversation. Thanks for spending all the time explaining all this wondrous insights to us. And look, I will say, as an audience of one right here, you've inspired me. I'm going to go read some of these papers. These ideas sound extremely, and especially the connection to string theory in terms of the way in which you may need the vertex operator construction of string theory within a
Absolutely.
four-dimensional setting is very interesting to me.
Absolutely.
So, and look, best of luck with the experiments, man. If we can detect that right-handed neutrino dark matter or
Right.
anything like that, how fantastic would that be? So, best of luck and look forward to having future conversations. So, thanks for joining
Thanks
us.
so much, Brian. Lovely to see you.
Bye.
Thanks.
Thank you. Bye.
Bye.